Thank you for staying with us for the last session today. And we came up with the title of the session in no uncertain terms. We have the privilege of having two excellent speakers here this afternoon. Alfredo Maldonado, together with colleague Masaki Itagaki.
He's a co-author, but he's not here.
Yeah, he's not here today.
He's in the States, actually.
All right. And Alfredo who's an old colleague of ours in the LRC and friend, who's developed some automated terminology software that he's going to talk about. But before he does that, we will hear from Alfredo about checking terminology consistency with statistical methods. It's a very interesting topic, and it's one that is being pursued by a special group in Microsoft that is based both in Redmond and in Dublin. And I'm looking forward to find out of the work of this group, and just talk to Alfredo, and he has promised us a paper for localization focus, so we will be able to read more about this work very soon. Thank you very much for coming, and please welcome Alfredo.
Sure that I'm on time. Thanks very much. So just a little bit about me. I work in the Language Excellence Department here in Dublin. And we're a team that we have terminologies. We basically manage terminology, and we define some language standards for Microsoft. We have several people also based in the US. My boss is actually in the US. And we also have in-country terminologies scattered around the world. So I'm just going to start with my presentation. So I'm going to first do a brief introduction of why we're doing this, what's our motivation to do this. Then I'm going to start talking about our process, the actual technique that we use, what we call internal consistency check, and I'm going to say why we call it like that, which consists in 3 steps, which I'm going to talk about them in their own as well. After that, I'm going to talk about some current changes, because I don't think our method is perfect yet, but we are seeing some benefits already. We're seeing some results. So we think we're doing the right thing, but we still need more work and research as well on this. Some tips in case you want to try this at home. Don't try this at home. You want to develop your own methods. Some tips that we learn. And some future improvements, basically some of the things that we want to, one of the challenges that we have right at the moment that we want to tackle in the future. And so just to get started, why terminology consistency? What's the fuss about having the terms that are consistent? Well, it's one of the key elements of that customers perceive of language quality, of localization language quality. So it's not the only element. There are other elements such as accuracy, that the text is fluent, etc. But when you're talking about technical terminology, you want to get it right. You want to be consistent as well. So we want. That's why we're focusing on this with this tool. That's why we're investing time on this tool or in this method. Terminology consistency is very important, but it's also quite difficult to maintain. So, because many people work on the project at the same time, people based in different countries sometimes, or different companies as well. There's products that have more than one localization vendor working for them. Also, it's hard to keep in sync source and target during the localization cycle, and even during the process cycle. Martin was explaining some of the problems earlier on. And also terminology changes all the time during the different versions of one product, because you get feedback from your market or from your marketing people, and you learn that you have to change a term because it's not already correct. It's not correct anymore, or for the Manual language UX can help. They can help with detect inconsistencies. However, they cost time and money. And they usually concentrate on a sample of the text of your localization file. So especially when you're talking about a very big product such as Windows or Office or Visual Studio, especially when you talk about content as well. If you can imagine the MSDN library content, for example, which is localized in majority, it's impossible to have this done reviewed by a human. And there are other restrictions, other problems as well. For example, the reviewer must be a professional, they must be experienced in the product, they must know the terminology, they must know the reference materials. So the pool of people that you can have could be reduced. Also, even if you have an expert, it's hard, it's a human being, it's hard for him or her to be able to keep track of terminology changes. And we've seen that many times. Because terminology changes all the time, and people are not just looking at the reference all the time, people miss inconsistencies. So our question is, can we use technology somehow to control consistency? And yes, the answer is yes. However, the tools that I'm aware of, or that I've been aware of traditionally, are based, or they need a term base or a glossary or a list of terms that you need to fill inside the term, inside the tool, before you can run it and get a report on the consistency. The problem is that not all software companies have term base or a glossary or managed terminology. And even the companies that we do, for example, Microsoft, we do managed terminology, is still a work in progress. We've used managed terminology for the last 5 or 6 years, and it's still incomplete. Every day or very frequently we have new products. We acquire products as well, and even legacy terminology is not well captured because we concentrate usually on the more visible terms or more important terms. So this approach our approach doesn't require a term base. That's what we do. So that's what we start from. However, you can attach a term base if you want, but what I'm going to explain today here doesn't require a term base. We do this by using the terminology that is already contained inside your localization file. For this, we mine it. We apply a term mining process. Basically, we extract terminology. We identify automatically terminology. And after that, we try to decide whether this terminology was translated consistently or not in the target side of your localization file. So that's why we call our approach internal consistency check, because we check the consistency of terminology in the localization file as it is, without taking into account any external reference, any glossary or any term base. It consists of 3 steps. The first one is, as I said, the mining of the terminology, identifying terminologies. The second one consists in identifying the translation of those terms that we mine, and we have to determine the translation on the column side, and that's kind of the most complicated part of the algorithm. We call it alignment. And the third part, which is the easiest, is just check the consistency, whether the translations, all the strings comply with the translation that we identify or not. So just to help you visualize this process in a graphical way, I created this little animation. I hope it works. And basically the first step consists, as I mentioned before, it consists in identifying or mining terminology. So here I'm running a process to identify this terminology, these terms, and I have highlighted them there in green. So I'm talking about terms, not strings. There are terms inside a string. The second step consists in aligning the terminology, that is, finding the correct translation of those terms inside the target side, inside the target string. And this is the trickiest part. I'm going to explain how this works. And the third is just to check the consistency. If you speak French, you probably will find that this is not a very good example. But here you will see that the translation for containing form is formula continuum, in this case as well, down below there, formula continuum, but in this case, it was translated as formula continuum, which is incorrect. So because it's the term that is that stands out is the one that we flag as inconsistent. So let's go drill down a bit into each of the steps. Step 1, source term mining. This consists in extracting what we call bigrams and trigrams. Bigrams and trigrams are basically terms made of two words and terms made of 3 words, respectively. We concentrate on noun phrases of the form noun, 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 noun. If you have the printout there, you should probably write them down because it's not visible in the printout. Just wanted to make a note that for some reason it didn't show. So that's the form that we are mining, that we're defining. So we're concentrating on nouns of those 2 forms: noun, noun, which is our bigram, and noun, 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 which is our trigram. We discriminate verbs and verb phrases, because we have found in our own database, terminology database, that verbs comprise only 5% of the total terms. Or similarly, adjective phrases, which can be valid terms, they only comprise 2% of the total terms. As you're going to see, these particular parts of speech are a bit tricky. So we discriminated. It's just an assumption or kind of like our basic, a little compromise that we have to do in order to create our model. So we try to capture the majority rather than capturing everything. We also discriminate monograms, that is terms, nouns made of only 1 word. The reason is because most of them are going to be common words, which are not necessarily technical terms. And as you know, any common word can have synonyms. And if we capture them, we're just going to get a lot of false positives. So it's a bit of a challenge for us because we might want to capture this at some stage, but at the moment we're not capturing. In the future, we want to cover as well the category of adjective plus noun. So just one thing. So in order to complete the source term mining process, we just run a part of speech tagger and identify these 2 forms: noun, 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 noun. That's all we want to say. On the source side, we never apply any grammatical analysis on the target side, because we deal with many languages, 13 plus for the standard products, and more than 100 if we start talking about the late language from that. So we don't have a good grammatical model for all the languages that we localize into, basically. So we have to focus on in English. That's why we apply this statistical method as well for alignment. So in alignment, our product statement process is given a source term S that we mine, we have to identify the correct target term T that in the translation column. So again, with animation, let's see that our mine term is input form, and we have some text here in French. What I need to do is to identify that input field, the translation of input field is trompe. That's what I have to do. How do I do that? Well, first I need to consider all the term combinations, what we call n-grams. An n-gram is a word of 1, 2, 3, or 4, n standing for n equals 1, and n equals 2, etc. So a monogram is an n-gram of 1, a bigram is an n-gram of 2, a trigram is an n-gram of 3, etc. So basically, I capture every single term combination in every n-gram, focusing in this example and just mining bigrams and trigrams, and each of these combinations is a candidate, is a term candidate. So what I need to do is to find out which of these term candidates is the correct translation. And just what I note here, languages such as German, other Germanic languages that tend to, you probably know about that tend to merge several words into one big word. You probably want to consider n equals 1. So this is part of the minimal language knowledge that you have to know about your target language. So, but for other languages you can consider n, 2, 3, or 4, maybe 5 for Spanish, for example, because Spanish will tend to put inside a lot of preposition, which we're going to see. So, how do we decide which one is the correct one? How do I know that in my bucket of candidates that I have here, which one is the correct term? Well, I use Bayesian statistics for that, and I use a probability, conditional probability theory, the conditional probability theory. So basically, now I already found my problem statement is given the source term S, I want to obtain the n-gram T, that is the candidate T, that maximizes this probability function. And the way you read this, I'm just going to do this part, is the probability of my candidate T given S. So given S, I know S, I want to know what's the probability of T. How do we calculate this? Well, just going a bit quickly, I apply some arithmetic or algebraic trickery using the multiplication rule of conditional probability just to get these formulas, basically, because I know how to calculate the three bottom formulas, I know how to calculate them, so with those numbers, I know how to calculate my conditional probability. So let me explain the three formulas. The first one is the probability of T. So what's the probability of T appearing? That T between bars means number of T. So it's the number of T, or the frequency of T in my text, in your localization file, divided by the number of n-grams of the same n as T. What does that mean? Basically, if T is a bigram, a term made of two words, you divide it by the number of terms made of terms that are made up of two words in your text. So it's just a way of what it is in person after. If T is a trigram, a three-word term, you divide the frequency of T by the number of terms that in total that are made up of three words. Okay, so it's just an important, it's mentioned there in the slides. The probability of S given T. We calculate this by something we call ST-seg. ST-seg is the number of segments where both S and T appear. So obviously S on the source side, T on the target side. I count the number of segments where both terms appear, and I divide them by the total of numbers where T appears. Obviously, there will be, if there are many T's outside this segment where both appear, that means that our candidate is bad. Why? Or how do we see that? Let me see if I can see the cursor also. So basically, if T appears outside where S appears, this number will be bigger than this one, making the result of this division small, a small number, a number close to 0. This would bring the whole result down, making the probability of the candidate low. So we discriminate the candidate. If both numbers are similar, that is that they tend to occur in the same way, in the same segments. If they're similar, the result of the division will tend to be 1. It will probably not be 1, but it will be close to 1, making the probability go up. If that's basically it. The other thing that I wanted to is that I'm not going to explain, but the probability of S is calculated similarly as the probability of T, but on the source side. And I'm not going to explain it because you'll see it in the next slide. We actually don't need it. So your task is to compute or calculate the probability for all your candidates. So in your comparison algorithm, in your comparison routine, you will be comparing TKs, and call it TK1, TK2, TK3. So in any statement or any cycle, you will be comparing the probability of TK minus 1 given S and the probability of TK given S. So basically the two neighbors. You can sort or whatever. But at the end of the day, what you're doing is this comparison. As you can see in this comparison, probability of S remains constant. So you can eliminate it because it won't affect your, it doesn't affect your calculation. You can get away with it. And you simplify the calculation and you probably save some computational time as well because as you know, we will be calculating this in a lot of candidates. So it's a lot of multiplications of divisions to make actually. So we just a convention that we have is that we call this result, we call this result I, just like I for index. So we call our equation or our deciding function, our index function is this one. ITK equals the probability of TK multiplied with the probability of S given TK. And the TK, the candidate TK, that has the highest I is our best target term candidate. So that's, we bet that that's the correct translation for the term. Now, some tricks, something called normalization. As you know, terms can appear translated slightly differently depending on the grammatical context. In this case, the term file name can be translated in several ways in Spanish. As you can see that there are articles and prepositions inside the terms, nombre del archivo, nombre de los archivos, etc. And they're not necessarily wrong, they're just different occurrences of the same term. So we need to, our algorithm has to be clever enough to detect that all of these are just different forms of the same term and not like an inconsistency. So we have to in order to reduce what's possible. We do this by using regular expressions. I'm not going to go into the regular expressions because they can be a bit complicated with mind later. But I'll just mention that you probably have to craft regular expressions for the different languages that you handle. In general, for Asian languages, and mostly Japanese, Chinese, the two Chineses, and Korean, we can get away with simple regular expressions, whereas for European languages, we have to craft more complicated regular expressions because of inflection that you get in the terms and the possibility of getting prepositions and other things inside between the terms. The third step is the easiest one, is just to compare, is just to get extract the strings that do not conform to the pattern that you generated. The regular expression pattern that you generated, you basically use it to detect the strings that are inconsistent. And that's a popular example from Italian. The last one is very funny because it's local computer locale, and it was translated as computer remoto, which is obviously incorrect. We have some challenges, so not everything is perfect. For example, one of the challenges that you can see at the top, again from Italian, is due to heavy rephrasing. So what is a false positive first? False positive is the tool is telling you the correct translation or the best target candidate that I found or that I determined has not been found in this string. This string is inconsistent. That's what it's saying. In reality, what happened here is that the term, in this case, client in Italian, has been omitted because the text, the string was heavily rephrased. And you can have an argument because in reality the text is a true translation of the source and is more easy to understand. It's easier to understand for the customer, the target customer, but it doesn't contain our intended terms. So this is one of the challenges that we have. Other type of challenge that we have is the monograms. That's why we discriminate them. When we apply our regular expression of the monograms, we get all sorts of junk, as you can see here. Only that which is involved is the correct one. The rest is completely unrelated words. that match these terms. So that's why we discriminate at this time, this stage, we discriminate monograms. Because if you concentrate on a bigram or a trigram, your regular expression will be stronger, will be able to match much more reliably the translation, the correct translation. But we probably will try to figure out how to solve this problem. We'll try. And actually, if you see the first example, due to rephrasing, that's also monogram, and it's a word that can be translated in different ways. So the two are actually related. Verbs, we also, at the moment, we do not work with them. First, because it's only 5% of them in our term base. So we estimate that the whole universe of terms in localizable text or material would be 5%. That is just an assumption, not very scientific. But the problem is that another problem that verbs have is their own inflection. You cannot work, while you can work a regular expression that can work across many languages for nouns, it is more difficult to do that for verbs. And for example, in the case of venir in Spanish, the word venir, it's not very easy to see how the conjugation goes, because sometimes there's an I that goes inside the term, that vienes. So you really need to have lexical data, or you have to have information about the target language, lexical information about the target language in order to capture verbs. And as I said, if you have 30 plus languages, or 100 languages, if you consider it, or I don't know how many more, this is more difficult. So this is one of the challenges that we have. Another challenge that we have is the languages such as Arabic and other complex script languages, languages that reflect on for example, on the first part of the word, on the prefix rather than the suffix. As you saw, our regular expressions rely on the suffix, not on the prefix. So we have problems with those languages. We also have, one of our challenges is our best candidate selection logic. The same logic that I explained. We found that around 70% of the candidates are selected correctly. Here on this side, you can see a good list. You can see the I. The I at the top is the highest, the I at the bottom is the lowest. So this one you can see that the first one is actually the correct translation. The other ones you can see that are just partial or incorrect translations. But it fails in some times. For example, if you see type argument, the correct translation is affluent and deeper. And the probability, or the I, is much lower than the first candidate argument, which is an incomplete term. So these are due to collocation phenomena and other things that we have to tackle. So this is one of the problems that we currently have. Just some tips if you want to try this at home, as I said before. You have to have, if you want to try this out, your data has to be clean. It has to be well aligned. It has to be clean of any HTML or XML tags. If you have non-localizable strings or strings that are not localized for whatever reason, remove them, because they will just, you won't find it won't work. The method won't work. If you handle Asian languages, you have to run a word breaker. You have to use a word breaker too. We have that. We actually use one that's already included in Windows. We just call it library, and hopefully it works. And otherwise, if you don't use a word breaker, your n-gram handling won't work. Something that we found is that even if I said at the beginning that this can do with some term mining, that sometimes if you craft a list of terms, if you create a list of terms, you can get very good results. We have found this a lot. But the terms have to be well selected. A well selected term is a term that has a precise technical meaning. For example, if you see failure and data, they're good terms, but they're not. They're actually bad terms because they're first in monograms, as you know, the matching, pattern matching issue. They will have a pattern matching issue. And also, they're too generic. They could be part of other terms, or they run the risk of being omitted because they don't carry much semantic value. Whereas good technical terms like work and process, user account control, a term that conveys a specific concept, these kind of terms will tend to perform better with this selection. And finally, the more data you have, the more accurate the result will be. So if you have a very small project or a very small product, you're probably just better off by doing manipulation. If you have a big project where a lot of content, it's better if you can benefit from this. So, excuse me. Something that we recommend, for example, is mixing software material from user education material or help material, basically software with content. This just to bring up the number of term repetitions. So this is something that we'll try. And just the last slide, efficient improvements, things that we want to do in the future. We want to work with adjective plus noun, this pattern, and we think that we have some promise of success in that area. We want to work with verbs, at least to experiment a little bit, even if we probably require some lexical data, but just something we want to do. And we want to add something that we must do as well, is to add support for more other languages that do not inflect on the ending of the word, like complex languages, Arabic and so on. And we have to, sorry, that's the time I And we want to also improve the best translation candidate selection logic. And that's it. I don't know if you have any questions. So we get the best target candidate, and we generate the regular expression from it. So basically, we take we do several tests per language. So we try to find an optimum per language. So for example, an arbitrary case would be just remove the last 3 characters from the word, say that you have a 2 words, it's an Italian term, codice errore, for example. So I remove the last 3 letters from one word, the last 3 letters from another one, and I accept up to 3 or 4 more letters to be added. If it's Italian or Spanish or French, for example, I also accept that people can enter a preposition and an article inside, up to, I think, 4 for the case of Spanish. So, and obviously I expect, or I assume that a preposition will be a short word, say a word of maximum 2 or 4 letters. For example, para in Spanish would be the biggest one. You know, that kind of thing. So we have a bit of a logic there. That's what we call the minimalistic language knowledge that we do. So we do not do any grammatical or any lexical analysis on the target side, but we know more or less how each language behaves. And so, well, a group of languages. And we try to generalize. For example, I apply the same logic for Spanish, French, and Italian, for example. and try to just hope for the best. So we generate evaluations, obviously, of matching evaluations. We send them to our terminologists or other people that know the language, or sometimes the localization vendors as well. We get feedback from them, and then we refine the logic around that. So it might not be 100% perfect, but it's working so far for some languages.
My name is Josef von Genabit from Dublin City University. For the work that you've done, could you have used a standard statistical machine translation technology? I mean, just the phrase alignment, word alignment models that you get from that. I mean, they do, some of the work is very similar to what you present.
We consider that at the beginning. Actually, when my boss started thinking about this project, the other author of this, but we found that because we don't have many repetitions, usually those statistical analysis or the traditional analysis focus on huge corpora. We're talking about here more of software projects that some of them tend to be big, but they're not as big as a corpus. So because of that, we have to kind of tweak the algorithm a bit, and that's why we also rely on regular expressions and things like that. So that's why we here apply the full word alignment.
This is Anna Aguilera from JavaScript. Thank you, Alfredo, for the presentation. It was very interesting. My question was, after you find the best candidate, do you actually use those terms to improve the legacy material automatically, or is just an advice for future projects?
Well, at the moment, we don't do anything. We're still working. Well, we have some ideas. We have some ideas of using this for, well, basically what we're doing at the moment is more like trying to clean up the product. Just that. That's the immediate goal at the moment. But we have some ideas, for example, for creating legacy, capturing legacy terminology. That's one of the ideas that we have in the pipeline. One of the problems that we have at the moment is that, well, we started managing terminology 5, 6 years ago. So obviously we concentrate mostly on the new terminology, new terms, but we don't concentrate, there's a lot of terminology that is there. There's basic terminology, but it's there in the products. But that we assume that localizers know it, but you shouldn't assume that, because from time to time, even those established terms can change. So we want to identify as well something more in the future. We want to mine or identify automatically legacy terminology and eventually add it to our term base. Yes.
My name is John Warren. I just have one question. You mentioned words like data and failure as sort of ambiguous terms that appear in lots of different contexts.
Yes.
Do you blacklist them to avoid false positives, to reduce the number of false positives?
That's something actually we're going to do. We're going to allow, because even with all of these, we still get false positives, even from the 2 grams and 3 trigrams, especially because, as you saw, the logic fails for some of the terms. So that's something that we're implementing as well. There were other people.
We can have 1 or 2 more questions. Move on to
So it looks like you use a part of speech tagger as well.
Yes.
And does Microsoft also have lemmatizers for these languages? Because if you could use them, if they were reliable, you could save a lot of work for the regular expressions.
Yeah.
Cut it down.
We have for some languages, but we don't for all languages.
Yeah. And have you tried it for the languages you have it for?
Sorry?
Have you had a chance to try it for the languages that you have the lemmatizers for?
We could, but we have tried with Japanese as well, but not much. We haven't got to that part. The reason is mostly because we have to, we don't have much time to experiment, basically. We have to, we have people waiting for something. So it's like, okay, this works, there you go. That's the approach, but that's a good point. We should probably experiment with other languages. We probably will. The The problem is that whatever experimentation we do in Spanish or Japanese will probably not be used for other languages that we don't have a target for or any algorithm for. Probably we never will unless we acquire or license it from a third party company.
Yeah, my question was very nice though.
Yes, who you are, where you're from?
My name is Nikiforos Karamanlis from TCD. Once you have spotted the inconsistency, do you actually try to correct the strings, or do you stop in having a corpus which is presumably inconsistent? In other words, the question is, do you actually go back to the person who translated it, told them, you've been inconsistent here, can you please correct it?
What we do at the moment is we just generate our report in Excel and send it to the translator.
Oh, you send it back to them?
Yeah, that's what we do. We have some ideas as well. For example, another idea that we have is that when the translators can run it themselves, just to check their own work, It's like just like running a spell checker in a way, That's what we are selling this tool to our own localization providers. You can check your own language quality for free. And something that we're also trying to do or trying to see is that we can integrate it with our other tools, like for example some of the tools that Martin was explaining. If we can run automatically and generate statistics, something that we also thought about creating is to, it's a statistical method, but still kind of gives you an idea of how good the consistency is, to a certain degree inside the product. So could we generate a score, a consistency score, and say which ones are the best, the product with the best score, or the language score, the best score, the worst score. And for example, you could use that score to select the projects or the languages that have to go through a thorough manual QA. And the ones that have a good score, well, you should save some money.